Okay, now that we have the Cauchy Riemann equations, it's time to look at some properties of complex differentiable of analytic functions. And, well, that will still be some abstract theorems that follow directly from the Cauchy Riemann equations. That's why these two topics, analytic functions and harmonic functions, are still lumped into this presentation. Well, let's take a look what we can get. First of all, if a function is analytic on a connected domain, and the derivative is 0 for every z in the domain, then the function must be constant. Well, that's something that we certainly remember from the real numbers. If you've got a function that's defined on a differentiable on an interval and has derivative 0, then that function must be constant too. And, well, basically connected domains are the analog of open intervals on the real line in the complex plane. Okay, so how do we prove that? Well, we use the fundamental theorem of calculus, and through the fundamental theorem of calculus, we can obtain for any 2 points x0, y0, and x1, y0 in the domain that u of x1, y0 minus u of x0, y0. Notice that, again, because y0 is the same in both of these inputs, we can assume that u is just a function of x, and as such it is differentiable, and so we know from the fundamental theorem of calculus that value at x1 minus value at x0 is the integral from x0 to x1 of the derivative, which in this case then is the partial derivative du dx of x y0 then, because of course that's the constantly held second component that we keep against dx. And similarly, if we want to take a step in the vertical direction, if we want to go from y0 to y1, let's say, and keep the x0 constant, well, then we can apply the fundamental theorem of calculus in the second component and realize that the value u of x0, y1 minus u of x0, y0 is the integral from y0 to y1 of the derivative in y, which is du dy, of x0, y dy. And because, well, let's see, the derivative is 0, and the derivative being 0, that means that du dx and du dy are both 0. That means that u does not change along horizontal or vertical lines inside that connected domain. And similarly, v also does not change along horizontal or vertical lines. And that means if u and v don't change along those things, then f does not change along horizontal or vertical lines. And now we're going to use connectivity. Remember that if we have any 2 points in a connected domain, those things can be connected by a path. The definition said polygonal path, but that doesn't really matter that much because polygonal does not necessarily mean that the path has pieces that are horizontal or vertical only. But anytime in an open set when we can connect one point P to another point Q with a path, then we can actually make that same connection with a path that is made up of horizontal and vertical pieces. You just have to make sure that anytime you get too far away from the path, as you can see here, anytime you get too far away from the path, you turn the corner and get back to the path. And so that means any 2 points in a connected set can actually be connected by a path that is made up of horizontal and vertical pieces, and then if f has a certain value at p, that value doesn't change as we go horizontal, vertical, horizontal, vertical, horizontal, vertical, and so on and so on. That value doesn't change along that path all the way to q, and that means that the function must be constant because no matter what p and q are, f of p will be equal to f of q. That result, well, and here's just a quick example thrown in for variety. I'm certainly following the text, and this is not meant to say anything bad about the text. It's a nice reminder, even though the example feels out of place. If we want to determine where the function f of x equals 3z squared plus 5 over z cubed minus 2 quantity squared z to the 4th plus 16 cubed is analytic, it turns out there is no need to compute the derivative, and we also don't need to use the Cauchy Riemann equations. And basically what we have to remember, especially in these abstract courses, is that just because we have new tools does not mean that the old ideas are discarded. As we are going deeper into mathematics, even though calculus already certainly requires a good bit of synthesis. In calculus, you can still cut things apart in certain ways that well, in certain sections, we only use certain kinds of tools. In an advanced class, all the tools that should be fair game to be used just about any time. And that's the case here because by the product rule, quotient rule, and chain rule, this function is analytic on its whole domain. And that means it is analytic except at the places where the denominator is not defined. And that is the case at the third root of 2 and the two other third roots of 2, which are third root of 2 e to the I 2 pi thirds and third root of 2 e to the I 4 pi thirds, as well as at the fourth roots of negative 16, which are the 2 e to the I pi over 4, 2 e to the I 3 pi over 4, 2 e to the I 5 pi over 4, and 2 e to the I 7 pi over 4. Okay, let's get back to some more abstract stuff. Take an analytic function on a connected domain and assume that its conjugate is analytic too. Now remember, that's not something that comes out of a chain rule because conjugation is not differentiable. And it turns out that we're getting another verification that the conjugation is not differentiable because the only way this can happen is if the function is constant. And the proof comes from the Cauchy Riemann equations because if we apply the Cauchy Riemann equations to, on one hand, the function, as well as its conjugate, on one hand, we get du dx equals dv dy from what happens to the function f. We get du dy equals negative dx, still from f. And we get du dx equals d dy of negative v, so that's negative dv dy. And we get du dy being negative d negative v dx, and so the negative goes away, so that's du dy equals dv dx. But that means that du dx equals dv dy, which is negative du dx, so du dx is equal to its negative. And similarly, for all those partial derivatives, these equations show that every partial derivative is equal to its own negative, and that means all partial derivatives are 0. And that means f prime is equal to 0, and that means that f is constant. And that's the end of this one. Similarly, if you have an analytic function on a connected domain so that the absolute value is constant, well, then the function is constant. Now that's basically because differentiability means you can't just tweak the e to the I theta just a little bit, but unlike what we're doing on the real line, where if the absolute value of a differentiable function is constant, the function must be constant because you can't just jump to the negative without punishment. This is no longer so obvious because here, of course, e to the I theta is something where you can just make a little wiggle in the theta and the function would still stay constant if I were to multiply it with a little e to the I theta. But it turns out, because you see f times f bar is f absolute value squared. That means that f bar is f absolute value squared over f, and that would be analytic. And by the preceding result, that means that f must be constant. Now you could say, what happens when f absolute value is equal to 0? Well, when f absolute value is equal to 0, then the function is equal to 0, and that's it. So there's no problem there. All right, let's talk about harmonic functions. A real valued function of two variables is called harmonic if and only if it has continuous first and second order partial derivatives, and it satisfies the equation second derivative of u with respect to x plus second derivative of u with respect to y is equal to 0. Now this is not just a notion that is tied to 2 dimensions. So if you had 3 dimensions, you'd add a second derivative in z to that whole thing, and that would have to be equal to 0. In 4 dimensions, you'd add a second derivative with respect to the fourth variable, and so on and so on. So this is truly a very multidimensional notion. This equation is called Laplace's equation, and Laplace's equation describes steady-state heat transfer as well as steady-state wave motion, because the 2-dimensional wave equation is second derivative in x plus second derivative in y is equal to some number times the second derivative with respect to time. And so this is basically, if the right side is 0, that means your second time derivative is 0. So that means this is a wave that doesn't accelerate. This is a wave that has constant velocity, and that's about as steady state as waves can get. And the two-dimensional heat equation is d2u dx squared plus d2u dy squared being some constant times the derivative with respect to time. And if that time derivative is equal to 0, that means that your heat distribution does not change over time. So let's see, that was rather rapidly. We're not going to talk about these equations for a while, and when we talk to them again, we will actually derive them. The idea here is, in the heat equation, U gives you the temperature as a function of space, x, y, and time t. And in the wave equation, it tells you the height of the wave in terms of space, x, y, and in terms of time t. And these equations then, of course, are also special cases of higher dimensional equations. And the only thing that changes is that in 3 dimensions, you'd put a second z derivative on the left side. In 4 dimensions, you'd put a second derivative with respect to the 4th variable on the left side, and so on, and so on. So this is why Laplace's equation is very important. In the theory, it describes the steady state of rather important real-life phenomena. Okay, so let's see, what can we do? Just to get used to it, show that the function e to the negative y sine x is harmonic for 0 smaller x smaller pi and y greater than 0. Well, that just gives us an open domain. And if we just take those second derivatives, well, the second derivative with respect to x, let's see, derivative of sine is cosine, derivative of cosine is negative sine, so we get e to negative y times negative sine x, plus the second derivative with respect to y. Well, the second derivative of e to the negative y, the first derivative is negative e to the negative y, the second derivative is negative e to the negative y, so that's just e to the negative y times sine x here, because of course the sine x doesn't change with respect to y, and when you add that you get 0, and so the function is harmonic. If you've got a complex function f of z equals u plus iv of z, if that thing is analytic on its domain D, then its real and imaginary part are both harmonic on D, and that is really the key connection between harmonic and analytic functions. And the proof, well, complex functions that are analytic have only one derivative. We will actually prove a little bit later that analytic functions actually have derivatives of arbitrary order, and that means that the second and all the other derivatives also exist. As this course approaches the theoretical part still with a bit of a calculus notion, I don't have qualms in doing this here. However, in a fully axiomatic course, I would delay this result until we've proved that analytic functions really have arbitrary derivatives. Nonetheless, the computation then is not that bad. To prove something is harmonic, you have to prove that the second derivative in x plus the second derivative in y add up to 0. Well, the second derivative in x is the first derivative of the first derivative in x. The second derivative in y is the derivative of the first derivative in y. And now we know du dx is dv dy, and we know du dy is negative dv dx from the Cauchy Riemann equations, because this thing was analytic, right? And, well, that's just d2v dxy, dx dy minus d2v dy dx, and we know that mixed partial derivatives can be taken in any order. So that means that that's equal to 0. And that means that u is harmonic, and v, the harmonicity of v, is proved similarly. And so that proves this result. Okay, example. Well, the real and imaginary parts of f of z equals 1 over z cubed are harmonic, as long as xy is not equal to 0, 0, as long as we're not at the origin. Well, clearly because at the origin things blow up. And the neat thing here is, okay, we're proving an example here. Well, we're proving this, what we're claiming here. We only have to realize that f is analytic away from the origin, and that is something that can be proved with difference quotients or with a combination of the power, well, with the quotient rule, if you wish, or with the chain rule, which is typically how mathematicians would like to do it, because using a quotient rule with a complex numerator is a little bit funny looking. But either way, f is analytic away from the origin, and that's the end of that story, because we've just shown that real and imaginary parts of analytic functions are harmonic. So we didn't even have to determine what those real and imaginary parts are, which is again something that is very nice, because now we know anytime we've got a complex differentiable function, its real and imaginary parts give us harmonic functions, and so we get a lot of harmonic functions, well, sort of for free, or at least for a lot less work than satisfying Laplace's equation directly. Okay, if you've got two harmonic functions on a domain D, then the function v is called a harmonic conjugate of u if and only if we've got du dx equals dv dy and du dy equals negative dv dx. So if and only if the Cauchy Riemann equations are satisfied. And the theorem then is that the complex function u plus iv is analytic on its domain D if and only if u and v are harmonic and v is a harmonic conjugate of u. Well, the proof that analyticity implies that u and v are harmonic and harmonic conjugates follows from the preceding result and from the Cauchy Riemann equations, of course. And the proof of the converse follows from the fact that the Cauchy Riemann equations and continuous partial derivatives implied analyticity. So this is actually very quick, even though at first it looked as if we have to wade through a lot of muck in terms of partial derivatives and all sorts of things. No, we don't need to do that here, because now we have all these powerful tools at hand. The neat thing then is, or well, one of the neat things is that we then can also find the harmonic conjugates. So for example, that function u of xy equals e to the negative y sine x, which we had shown to be harmonic directly earlier on, we can find, on the domain 0 smaller x smaller pi and y greater than 0, we can find a harmonic conjugate for that thing, because we know that dv dy must be equal to du dx, and du dx is e to the negative y cosine x, which means v, if we integrate in y, this is the integral e to the negative y cosine x dy, which is negative e to the negative y cosine x, plus some constant. Well, that's not really a constant, that's a function that depends on y. So this is very similar to how you compute potentials in multivariable calculus, how you get a function back from its gradient, for example. And that's because it's exactly the same idea. These functions u and v are essentially potentials also. Dv dx is negative du dy. Well, that would be du dy is negative e to the negative y sine x, and the double negative makes the negative sign go away, which means v is the integral of this thing in terms of x. Well, the antiderivative of the sine is the negative cosine, so we get again negative e to the negative y cosine x plus some constant that can depend on x, so some function of x. Well, and now just like when we're computing potentials, we look at the stuff that is the same in both, and we write that down, but we don't add. So this is not twice that. This is just anything that's doubled up is just reported once. If there was something here down here that depended only on y, we would also put that up here or down here. But here, of course, as we match this up, we just get that the harmonic conjugate is negative e to the negative y cosine x, and that is something that can be verified directly if you wish, because you can always just go ahead and compute the partials of v and verify that those things are that the partial derivatives of u and v satisfy the Cauchy Riemann equations. Okay, that's it regarding the Cauchy Riemann equations. Certainly plenty of stuff to work with, especially for harmonic conjugates at the end. Remember, if the computation doesn't quite work out right here for you, just go ahead and write down what you think the conjugate should be, and then take the partials to make sure to double check. Other than that, thankfully we're now going to go into a more computational / geometric part of the course. I think we've earned that because we've done quite a few abstract proofs, and the other thing I've earned is I'm going to eat lunch again. If we have any 2 points in a connected domain, those things can be connected by a path. The definition said polygonal path, but that doesn't really matter that much, because polygonal does not necessarily mean that the path has pieces that are horizontal or vertical only. But anytime in an open set when we can connect one point P to another point Q with a path, then we can actually make that same connection with a path that is made up of horizontal and vertical pieces. You just have to make sure that anytime you get too far away from the path, as you can see here, anytime you get too far away from the path, you turn the corner. Okay, now that we have the Cauchy Riemann equations, it's time to look at some properties of complex differentiable of analytic functions. And, well, that will still be some abstract theorems that follow directly from the Cauchy Riemann equations. That's why these two topics, analytic functions and harmonic functions, are still lumped into this presentation. Well, let's take a look what we can get. First of all, if a function is analytic on a connected domain, and the derivative is 0 for every z in the domain, then the function must be constant. Well, that's something that we certainly remember from the real numbers. If you've got a function that's defined on a differentiable on an interval and has derivative 0, then that function must be constant too. And well, basically connected domains are the analog of open intervals on the real line in the complex plane. Okay, so how do we prove that? Well, we use the fundamental theorem of calculus, and through the fundamental theorem of calculus we can obtain for any 2 points x0, y0 and x1, y0 in the domain that u of x1, y0 minus u of x0, y0. Notice that, again, because y0 is the same in both of these inputs, we can assume that u is just a function of x, and as such, u of x0, y1 minus u of x0, y0 is the integral from y0 to y1 of the derivative in y, which is du dy, of x0 comma y dy. And because, well, let's see, the derivative is 0, and the derivative being 0, that means that du dx and du dy are both 0. That means that u does not change along horizontal or vertical lines inside that connected domain. And similarly, v also does not change along horizontal or vertical lines. And that means if u and v don't change along those things, then f does not change along horizontal or vertical lines. And now we're going to use connectivity. Remember that it is differentiable, and so we know from the fundamental theorem of calculus that value at x1 minus value at x0 is the integral from x0 to x1 of the derivative, which in this case then is the partial derivative du dx of x y0 then, because of course that's the constantly held second component that we keep against dx. And similarly, if we want to take a step in the vertical direction, if we want to go from y0 to y1, let's say, and keep the x0 constant, well, then we can apply the fundamental theorem of calculus in the second component and realize that the value